Thanks for coming to the lecture on selecting research participants, part 1. This is the lecture that corresponds with chapter 5 in your textbook. So this is included in module 3, again along with chapter 3, which is about defining and measuring variables. Together, these two chapters really focus on, and in fact this whole module focuses on the methods section of your manuscript. So remember the two critical, very common subsections of the method section are the participant subsection and the materials subsection. The last chapter that we covered, defining and measuring variables, really addresses the issues that will be discussed in your materials subsection. This chapter on selecting research participants is going to address issues for your consideration in writing your participants subsection. One thing to keep in mind when you are writing that subsection is that in addition to the items that measure your variables, which for most of you will be 2, okay, you will have items that measure your X, items that measure your Y, or items that measure your dependent variable, because that's the variable that's measured in an experimental design. So either way, you're going to be measuring either 1 or 2 variables. And you'll have items that measure each. And how you present them in a questionnaire is completely up to you and up to your own strategy and the goals of your research project. So if, let's say, you're measuring self-esteem and body image, you might have all the self-esteem items together. You might have all the body image items together, or you might mix them. Or some people even mix items that are not related to the hypothesis in order to stop participants, say, from giving too much thought about the way they respond to the items. Those are up to you. But with respect to your participant section, you will also be adding what are called demographic items to your questions that you are handing out to the participants. And those items are items that ask participants to describe themselves with respect to characteristics that are used to categorize them. We still are into categorizing in our society, and so how do we do that? Well, we will ask participants to report their gender or their age or their maybe socioeconomic status, what region of the country they live in, what's their educational level, what's their ethnic identity. Those kinds of questions are considered demographic, and those questions are the ones that you will be using in order to describe your participants in that methods subsection of the method. Okay. So there are lots of other issues related to sampling besides the demographics, and that's also what we're going to be covering in this lecture and in part 2 of selecting research participants. A lot of this information regarding sampling should be familiar to you, and that's because you've either taken stats or you are in stats right now, because it's a co-requisite or a prerequisite for this class. And sampling techniques are central. They're very critical to central limit theorem, which is the primary theory that underlies all of the statistics that we use in the behavioral sciences. So that presumes that all human characteristics are distributed normally. Okay, so moving on, just a couple of quick announcements for you. One is that along with your regular lab assignment, you soon have a writing assignment that is due in lab. It's submitting the introduction draft. I've spoken about this quite a bit, both in lectures, and presented some material to you regarding the draft of your introduction in lab. There is a rubric posted in the assignment in lab, and you would be well to review that rubric pretty extensively before you submit the draft of your introduction. Your introduction draft, of course, follows the outline that I've given you for the introduction section of your manuscript, and that includes a broad statement of the problem, a review of 5 primary sources, and the concluding paragraph, which contains your hypothesis, information about your variables, and your population of interest. So don't forget that that is also coming up due. So there you go. Introduction drafts are due very soon. Submit in lab. All right, so the objectives for this unit include these. You're going to understand the difference between a sample and a population. Most of you probably already have something of a grasp on that, so I'm not going to beat that to death, but really understanding all the implications of samples versus populations is important, so we will talk about that. You should be able to differentiate among probability and non-probability sampling techniques. Different textbooks have this organized a little bit differently. In our textbook, they break all the sampling techniques into these 2 different types, and so, or general categories, I guess you could call them. Probability techniques and non-probability techniques. Non-probability techniques are by far the most commonly used, but there's more probability techniques, and those are really better techniques to use. But keep that little framework in mind, if you will, that they're sort of organized in those 2 different general categories. And then of those different methods that are in the probability and non-probability categories, we're going to talk about their different rationales and also about their strengths and weaknesses. There is one clear winner in the contest of best sampling techniques. There's a clear winner, and I think there's kind of a clear loser too. But there's other considerations, just like with measurement. You know, with measurement, it's a trade-off of strengths and weaknesses. You know, even sometimes you might have to give up having a very good measure with respect to psychometric properties for more practical concerns like the expense of it or the ease of its use. And the same thing applies to these different sampling techniques. There is one kind of clear gold standard, but you can't always use it for practical reasons and methodological reasons. And it's also, of course, because it's the best one, more difficult to achieve. Isn't that always the case? So we're going to be talking about those different rationales as well as strengths and weaknesses. So here's the general outline I have for you. I'll give you a little introduction to sampling and the sampling techniques, and then we'll talk about that category of probability sampling techniques, then the category of non-probability sampling techniques. We'll discuss the issue of external validity. Here is that word validity again, and this might be a good opportunity for me to tell you that you're going to run into the words reliability and validity a lot in research methods. However, they don't always have only one definition, and this is an example of it. We just got done talking about defining and measuring variables and validity of measurement tools, okay? And there was all those different kinds of validity. Remember, there was face validity, concurrent validity, predictive validity, et cetera, et cetera. Well, validity has a broader definition outside of just measurement, okay? Validity itself means the truth of something, the veracity of something, the accuracy of something. So when we're using the term validity in the context of measurement, we're talking about the truth value of that measurement tool. Now we're talking about validity in the context of sampling and research design. So external validity is going to be talking about the truth value of your research design and your research findings, okay? So keep that in mind, that you're going to see that term validity over and over and over again, and this is not the last you're going to see of it, but that it has a little bit different meanings and it appears in different contexts. And then conclusion. Okay, so introduction to populations and samples. Now, this is the part that should be familiar and somewhat comfortable to you from your statistics class. And that is that when you hear the term population, that is referring to all cases of interest. Okay, so what is a case of interest? Well, the answer to that question is the same as the answer to this question. To whom do I wish to apply my findings? So that answer to that question can sort of fall anywhere on a very huge continuum, okay? And that continuum sort of has tiers to it. So you might wish to apply your findings to college students, okay? College students is a very vast and diverse group of people. That would include 4-year attendees, 2-year attendees. Would it include people who are attending, say, vocational schools or colleges? Possibly. It would apply to people in a variety of ages, in a variety of different places in the country, applying a variety of different schools of different levels of selectivity. It would apply to Harvard, and it would apply to, Arizona State University. So if you are going to apply your findings to college students, that's going to apply to a very vast and variegated group of people. Now, you could also apply it to community college students, which is somewhat, more specific on the continuum. You could even get more specific and apply it to Mesa Community College students, or even yet more specific, if I was doing a study, and let's say I had an interest in teaching techniques with my students, I might even define that target population even more specifically to be my Mesa Community College students enrolled, for example, in my research methods class in the spring semester of 2019 or whatever. So the answer to that question, what is your target population, depends on your interest and the goals of your research. You can define it very specifically, you can define it very broadly, but it does have a direct bearing on, of course, who you will include in your sample. What do I mean by sample? Well, the sample is a subset of the population. So whichever people are actually participating in my study comprise the sample. And it almost always is necessarily smaller than the target population, but it doesn't necessarily have to be. And you will see the advantages and disadvantages of that in a little bit. So for example, perhaps my target population is college students, but I use as the participants in my study, my students registered in my research methods class in the fall of 2020, okay? That's my sample or my subset, drawn out of the population, or people who are members of that population, but on whom I actually perform my study. Conversely, if my target population is my research method students, then if my sample is comprised of all my currently enrolled research method students, then my sample pretty much overlaps with my target population. Now again, there are advantages and disadvantages to each of these different situations that I think will become clear to you in the next couple of slides. The most important consideration when you're talking about the relationship between a population and a sample is representativeness. So in the example that I just gave you, if my target population is all college students and my sample is my research method students, then I'm going to have some questions in my mind about to what extent those students currently in my class are representative of all college students. I'm going to just go out on a limb here and say probably not super representative. I mean, if you look at the demographics of a community college enrollment versus enrollment in, let's say, the average college across average colleges across the United States, I'm going to guess that maybe community college students tend to be more likely to be employed, maybe. They might be more likely to be returning students, and so hence they're maybe on average a little older. I'm guessing maybe they're more likely to have children and other family responsibilities. So, you know, I don't have direct evidence about that. Those are just examples, but I'm guessing that's probably the case. Now, that doesn't mean we don't have a lot of students at Mesa Community College that are very much like the average college student across the United States. I'm just saying that as a group, my sample might not share the same demographic characteristics to a T that all college students did. But if my sample is Mesa Community College students, my community college students, and that is also my target population, the people to whom I wish to apply my findings, then in that case, my sample is perfectly representative because my sample and my target population are the same. Okay. Again, we're going to talk more about the implications of this in a little bit. So, a couple of other considerations when you're thinking about representativeness. One is called the law of large numbers. The law of large numbers is something that you should keep in mind when you are making a determination about how big a sample you want, how many resources and how much time do you want to invest in acquiring people to participate in your project. Well, the law of large numbers is why one criticism of studies, almost always students bring this up as a criticism, is sample size. That's like your go-to criticism. Unless the study is very, very large, then students will always say one critique is sample size. Well, that's because the law of large number states that the more people you have in your sample, in other words, the larger it is, the more representative it necessarily is going to be, because there's more opportunity to capture all those variations that occur in your target population. So from a statistical standpoint, what that effectively means is that your average distance between your population, your hypothetical population mean, and your sample mean on any characteristic that you're measuring is going to decrease as your sample size gets larger. Now, what does this tell us about sort of the optimal size of a sample? Well, there's a nice graph in your textbook that illustrates this for you. It shows you a graph of the average distance between the population and the sample mean plotted as a function of sample size or number of scores in the sample. And you can see that it's pretty dramatic, okay? So there's a very steep drop in that distance between one participant and I'm going to say about 30 participants, okay? After that, the effect slows down a little bit, and the benefit to having an increasing number of participants in your sample starts to decline. The benefit declines. Although you're still getting a smaller and smaller distance between those means, the effect isn't dramatic once you pass 30 participants. If you're not grasping this, as I probably wouldn't if someone were explaining it this way to me in words, I would want to see the visual. So go look at that graph in your book. It's on page 114. So basically what that graph is saying, that around about 30, the benefits of increasing the number of participants in your sample start to drop off. And so then you have to weigh do a kind of cost benefit analysis. It's going to take me more time, more effort to start getting more and more and more participants. So, you know, maybe I'm going to be happy with around 30, which is why I always recommend for student projects, shoot for 30, live with 25, basically. It's kind of a rule of thumb. Now, if you guys are doing this online, you might not even be collecting actual human participants. You might be using dummy data sets, in which case I will say, if you're fabricating a data set for your own use, go ahead and do 30 so that you can have a nice, robust example of hypothesis testing. The other consideration with respect to representativeness is the issue of external validity. This is a graphic of the relationship between the population and sample and the role of external validity in that relationship and in research design. So as you can see at the top, you've defined a population. That's all individuals of interest, all cases of interest. To whom do I wish to apply my findings? It could be all people diagnosed with schizophrenia, could be all women, could be all people. It could be that large, okay? Or it could be very specific, as I was saying before. You then acquire the sample selected from the population, okay? Now, that first arrow going from the population to the sample, that arrow consists of your sampling techniques, okay? That's going to be the topic of the next few slides. What are we going to do while that arrow is pointing from the population to the sample selected from the population? How are we going to acquire that sample? The next arrow going from the sample to the box below says the sample is the specific set of individuals who participate in the study. Okay, now you have them, you've acquired them, you run your study, and then the results from the sample are generalized back to the population. That statement on the left is the definition, one definition, of external validity, okay? And it is 100% related to the representativeness of your sample, which is 100% related to the sampling technique that you have used. So external validity is also sometimes called generalizability. And that is the degree of confidence that we have that the findings in this sample, okay, represent, or the findings in the study, even if you want to talk about it more broadly, that the findings in the study, or more specifically the findings of the sample, represent what is actually going on in the general population. That is the definition of external validity. Now here's kind of a real life example for you. Years and years and years ago, it used to be that a lot of the studies done on symptoms and treatments for heart disease and heart attack included mostly men in the studies. And that I don't know that it was necessarily for reasons of being sexist. It may well have been because your typical heart attack patient or sufferer is probably a middle-aged male, okay? Women do have heart disease, generally at lower rates than men, and so men were included in many of the studies. There's also some methodological reasons, as we're going to get to, for excluding one sex or another in a study. And that has to do with controlling of variables in an experimental design. So, I guess I have a hard time getting worked up over the fact when there are historical studies in which women haven't been included, because I think there were, in some cases, sound reasons for that. But when the reasons weren't sound, I see changes in that. And this example I'm giving you of heart disease is kind of a good example of it. But these studies were kind of finding that there were these various symptoms of heart disease or heart attacks, and they were oriented towards sort of helping people recognize those symptoms of heart problems, like, chest pain or pain radiating down your arm, shortness of breath, those kinds of things. And so, they sort of disseminated this information, like these are the symptoms to watch for. These are the symptoms you need to know. If you're going to have an impending heart attack, you need to know if this is a possibility, and on and on. Well, what they discovered over time was that apparently women did have higher rates of heart disease than they had realized. And part of it was because for maybe reasons of physiology, hormonal reasons, I don't know. I'm not a medical doctor, but women were experiencing and reporting the symptoms differently. So they now say that the symptoms of an impending heart attack can look a little bit different in women than in men. So these studies that they were conducting in samples that were primarily comprised of men did not generalize well to women. And so throughout the course of history and science, we've sort of now learned that perhaps in many ways, having a diversity in these samples is beneficial. There is a downside to that, though, as well, and you will learn about the downside of that when we get to experimental design. All right, so moving on. Continuing with our introduction, if you now understand that the goal is to acquire a representative sample, then your next question would be, well, how do I get a representative sample? What do I do in order to acquire a representative sample? Well, you want to minimize something known as selection bias. Now, sometimes when I ask students what they think bias means, sometimes they respond that it's like prejudice or discrimination. Well, bias could result in prejudice or discrimination, but in a broader sense, that's not the only definition of bias. Bias by itself just means non-random, okay? It means systematic. So, in other words, if you are using a biased means of selecting your sample, that means that each person in your target population does not have an equal chance of being selected for your sample. Okay, I want to say that again because it's very, very critical. Okay, selection bias, it means that there's some systematic process that you're using in selecting your participants that is resulting in a non-representative sample. In other words, your procedure is non-random, okay? If you are using a biased sampling procedure, that it doesn't mean you're being mean. It doesn't mean you're deliberately excluding people. I'm not talking about, some emotional-based motivation. I'm talking about just the procedure that you're using. For whatever reason, you're including participants that differ in important ways from your target population. They're non-representative. So, of course, your goal is going to be to minimize this bias. Now, the different techniques that we're going to be talking about yield different probabilities of bias. So some of these procedures are more biased than others, and that means they cause you to be systematically selecting people for your sample to an extent that they're going to differ in some ways from your target population. So think about that. If I want to apply my findings to all college students, but the way I'm selecting my sample is to just perform my measurement on my students, then you guys are going to differ in important ways, not every single way, but probably in some pretty critical ways from all college students. And those reasons I just highlighted a few moments ago. So different techniques are going to yield different probabilities of bias. By probabilities, I mean we're only making a hypothetical guess about this. You don't know for certain, which is why we have to rely on what we know about these different sampling techniques. However, all these different sampling techniques are potentially biased. You can never be guaranteed that your sample is completely representative of the population. You can only use techniques that minimize bias, okay? All right, so here are the two basic types that you see, basic sampling types. These are the categories I was talking about in the introduction page. So you have probability sampling techniques, that's one category, and then you have the non-probability sampling techniques. Now, you are only going to be able to use probability sampling techniques if you have a circumscribed target population. What do I mean by that? Circumscribed. It means that you know the number of cases present in your target population and they are accessible to you. Okay? So if your target population is all schizophrenics, let's say you want to conduct a survey or you want to do a study, let's say, on the best treatments for schizophrenics, best antipsychotic medications. Well, you're not going to be able to use probability sampling methods with that target population. Why? Because it's not circumscribed. You don't know how many schizophrenics exist in the population. I mean, we have CDC estimates. I think the rate in the general population is 1%, but that's only a percentage. You can't acquire and you can't know the number of cases of people diagnosed with schizophrenia. So that's going to exclude for you right out the gate using any of the probability sampling methods. However, you're not doomed, of course, because you can use a non-probability sampling method. Are those weaker methods? Do they yield higher rates of bias? Do they yield less representative samples? Yes. But lots and lots and lots of studies use them. In fact, there's kind of a running joke in psychology that, there's lots of jokes about psychology, but this is one of them, that psychology is the study of college sophomores. Why is that? Well, because college sophomores are ready, willing, able, and accessible people on whom studies can be run. Are college sophomores representative of the entire population? I bet you can think of a lot of ways that they likely are not. So there you go. Those are the two main categories. Okay, here's a little graphic that illustrates for you the relationship between the target population, the accessible population, and the sample. Now, the relative size of these different bubbles can be larger or smaller, okay? So generally, the target population is large, and like I said, it's all cases of interest. And then a smaller subset is the accessible population. And a lot of times that's too large for you to run a study on every person in the accessible population. And then even yet smaller is the sample, the people who participate in your study. Now, sometimes these are roughly equivalent. And in that case, you're going to have a very representative sample, but this can also move around. I can't show you this now because I can't do it in PowerPoint, but that little box of the sample could move around within that target population. It captures a different segment of the target population, okay? And that's where the issue of bias might come in. Now, here's another illustration of selection bias, okay? So let's just use the example of IQ scores. So IQ scores are presented in nice round numbers. IQ has high construct validity. The measurements of IQ and intellectual functioning are highly reliable and valid. They have good psychometric properties. And average IQ is represented by a nice round number to which everyone can relate, and that is 100. So we're going to use that as our example. So let's say you wanted to do a study of the effects on IQ scores of some sort of factor, like let's say small class sizes on 8th graders. Let's say that you thought smaller class sizes would have a positive effect on the IQ scores of 8th graders. So IQ theoretically is distributed normally, right? And by normal distribution, what I mean is that by definition, the average person, most people, have an average amount of something or an average level of something, okay? In that way, there's no shame in being average, because if you're average, you share that characteristic with roughly 52% of the population, okay? So what we have here is a little distribution which illustrates a normal curve, right? You should be familiar with that from stats, where over on the y-axis, you have the number of cases plotted against, on the x-axis, IQ scores, okay? But I have here scores on any quality or characteristic, because as I said earlier, central limit theorem rests on the assumption that all human traits, qualities, and characteristics are distributed normally. And that means, again, that most people are average. If you look at any concretely measurable human characteristic, that appears to be the case as well. For example, height, okay? Most people are, by definition, of average height. And I like to pride myself on the fact that I'm exactly average. I'm 5'4", and the average height for women is 5'4". And for men, and this is in the United States, I don't know what it is worldwide. For men, the average height, do you know what it is? It's 5'10", which I think is kind of interesting. And what is also interesting, I can't remember if I have this graphic coming up for you or not, but the standard deviation in height for men is much larger than the standard deviation in height for women. And what I find interesting about that is it comports with my own observations that when you see men just walking around, you know, living their lives, there's a lot more variation in the heights of men than women. Women's heights are all kind of clustered up at the middle, where you less frequently see very tall women or very short women. That just is not as common an experience, I don't think. Women tend to cluster up all around that mean of 5'4". And not to go off on a tangent or anything, but I was reading an article about this fairly recently. This is very curious to me, that studies that look at gender differences between men and women find that on a lot of traits, that pattern is present between the genders, where men and women may have even similar means. For example, on IQ tests, the mean IQ for men and women is 100. However, the standard deviations are different, and women tend to be clustered up more toward the middle of that curve, whereas the cases of men populating the extreme ends of that curve are greater, okay? But it both results in them having equivalent means. This is also where sometimes I tell my students that Discovery Channel, do you ever watch Discovery Channel? They make their living off the tail ends of the curve. So they always have these documentaries, and of course I'm addicted to them, where they like to highlight people who are in those tail ends of the curve on any different characteristic. And recently I had watched a show on primordial dwarfism, which is a medical condition. It's inherited. It's the gene for this is passed from, generation to generation. But it's a very rare form of dwarfism, which is unique from a different form of dwarfism, which is called achondroplastic dwarfism. And that is the form of dwarfism that the cast of Little People, Big World has, okay? And the people on that show, the Little People, have a form of dwarfism where they have a normal, some normal size features, like their heads are normal, the head size is normal, trunk size is normal, but it mainly affects the long bones in the arms and legs. But people with this form of dwarfism, where I was watching on the Discovery Channel, they had primordial dwarfism, which is that they are perfectly proportional. So they don't have it affecting certain areas of the body and not other areas of the body. It affects everything in their body. And they're very, very little people, some of them as small as 18 inches high. So my point being this, if you were plotting height on this normal distribution, those people would be very out, obviously, probably even more than 2 standard deviations below the mean, right? Because they are highly unusual. There are very few cases. But my point about Discovery Health was, like 2 nights later, I had watched a show on another condition, which was some condition of overgrowth that was a result of overstimulation of the pituitary gland. And it was called I can't remember what it was called, but they were highlighting this guy who lived in China who had this condition, and he was like over 8 feet tall. And so he was unusual as well, in that he was way over on the opposite end of the curve, right? Probably way more than 2 standard deviations above the mean. So people are very fascinated by these conditions because by definition, you don't see them very frequently. You don't encounter them. You much more frequently encounter average people who fall within that 52% of the population that falls within 1 standard deviation of the mean either way. So my point here being, here you have, an average IQ of 100. Well, if you were doing this study on 8th graders and you wanted this normal distribution to appear in your sample, well, then you probably wouldn't be very smart, let's say, to go acquire your sample from, a school for intellectually gifted kids, or maybe a school for kids who have intellectual disabilities. Okay, that will obviously result in a biased sample, and you're not going to be very confident when you then go try to apply your findings to the population in whom that distribution is normal. Okay? All right. I hope my digressions illustrate for you. That's all I can say. Yes, here I have that graph of heights of men and women. Okay, and this is what I mean by clustered up. Okay, so the average height for women, it shows here at 65 inches. I think it's actually 64 inches, which is 5'4", but you'll get the gist of it. And you can see, that curve is kind of more tightly packed around that mean. The standard deviation for women is lower, whereas more men cases appear in the tail ends of the curve. And so that curve is more flattened and more spread out, meaning that the standard deviation is lower. Hence, like I said, this might comport with your own observations that, you just see men of a more variety of heights, whereas with women, if you lined a bunch of us up, we're probably not having that much of a difference. All right. So what are the probability sampling methods? We're going to talk about each of these one at a time. The first probability sampling method, and remember, these probability sampling methods can only be used when the cases in your target population are known and accessible. And by known, I mean you can count them. You know how many there are, you know who they are, and you could access them, okay? And that is because simple random sampling requires that you set up a circumstance where every potential participant, in other words, every case of interest, has an equal and independent chance of being selected for your sample. So by equal, if you are shooting for a sample of 20, let's say, out of a target population that consists of 100 people, that you have to set up a situation where each person has exactly 1 in 5 chance of being selected for your sample. And furthermore, that the choice of one person doesn't influence your subsequent choices, okay? So what do I mean by that, by subsequent choices? Well, that illustrates the difference between simple random sampling with and without replacement, okay? So let's say, for example, I have this target population of 100 8th grade students because I'm doing my study on the effects of class size on IQs of 8th graders, okay? So I have this 100 8th graders. I've got their names, okay? I got it from the school, let's say. And so I put all their names in a hopper, and I'm going to draw out the names of 20 8th graders. That gives them all an equal chance, okay? They all have 1 in 5 chance of being selected. If I'm going to pick out 20 and there's 100 of them, right? 20 out of 100, it's 1 in 5. All right, I'm not the best at math, but I'm pretty sure that's 1 in 5. Okay, so independent and equal. However, the only way I can keep their probabilities equal is by, if every time I pull out someone's name, before I go to pull out the next person's name, I put the first person's name back in that hopper, okay, or that bowl or that hat or whatever it is, in order to keep all of those probabilities the same, okay? If I do not replace that person's name, then I'm violating the principle of independence and equality, because the pulling out of someone's name depends on the fact that I pulled out their name once already. Does that make sense? I'll give you a real life illustration of this. I found this article a few years ago and I found it pretty entertaining. Okay. I don't know. It's kind of a people complaining about their good fortune kind of a story, but this was actually in 2006, and it was such a good illustration of sampling with and without replacement that I kept the article and I always share it with my students. But it's an article entitled "Runner-Up Claims Mercedes is Hers." And what happened was, several years ago, the Chandler Education Foundation decided that they needed to raise some money, and so they set up a raffle, okay? And they sold raffle tickets for $20 each. And by selling these raffle tickets, they were raising money. And they hoped to raise a lot of money because what the raffle tickets bought you was the opportunity to win not just any old car, but a 2006, which at the time was brand new. Now it's probably getting pretty rickety. But it was a Mercedes-Benz CLK 350 convertible valued at $54,000. It's probably worth more now. But anyway, that was the prize for which they were selling the raffle tickets. And the purchasers of the raffle tickets were told that there would be a limited number of tickets sold. Okay, so there were only going to be 15,000 tickets sold. So basically, what the purchasers of these raffle tickets believed is that they would, for $20, have a 1 in 15,000 chance, right, of winning that Mercedes. Well, for $20, I don't know, maybe I would do it. Not that I love cars that much, but that would be a pretty good prize. So this gal, and her name was Mary Henry of Casa Grande, she bought a ticket for that chance to win the car at the foundation's benefit raffle. Okay, so wanting to make a big thing about this, the Chandler Education Foundation, and I'm probably embellishing this a little bit for entertainment purposes, but they put all these stubs of the raffle tickets in this giant hopper, okay? And they were at, I think it was Chandler Fashion Square, and they put all these tickets in one of those things that you use with bingo, you know what I'm talking about, where you roll it around and all the tickets get mixed around. And they decide for dramatic purposes that they're going to first choose a ticket for a person to win the runner-up prize of $1,000 because they want to build all the excitement, right, for this Mercedes. So they roll the tickets around and they reach into the hopper and they pull out the winner of the $1,000, and it's this Mary Henry, okay, of Casa Grande. She wins $1,000. Well, if I was Mary Henry, I'd be pretty happy. Everyone's clapping for her and everything else. And then they roll the hopper around again, and they build up all the excitement and all the suspense, and they reach in and they pull out the ticket of the person who wins the Mercedes. Well, Mary Henry is standing there like, what the heck? I paid $20 for an equal chance of winding up winning that Mercedes, 1 in 15,000, and guess what? I had 0 chance. So she filed a complaint against the Chandler Education Foundation and said, I didn't get what I paid for. Okay, well, this illustrates the issues with replacement and without replacement. She thought she purchased a 1 in 15,000 chance, but because they were sampling without replacement, they violated the principle of equal, and she had 0 chance. Now, usually when I discuss this in class, students will have a little discussion about what alternatives there could have been. For example, perhaps they should have pulled out the winner of the Mercedes first, right? That would have been better. Then everybody would have had a 1 in 15,000 chance of getting the Mercedes, and all the remaining people would have had a bonus opportunity to have a 1 in 14,999 chance of winning the runner-up prize of $1,000. That probably would have been a better strategy, okay? But what ended up happening is Mary Henry got told to sit down and shut up, and it was because there was some disclaimer at the bottom of the ticket that she purchased that said something to the effect of all decisions made by the Chandler Education Foundation will be final. So I don't know if she ever accepted the $1,000, but if it were me, I would have taken it and maybe gone on a little spending spree. So with and without replacement does have implications. Now, you're not going to be able to use with replacement if in your study the methodology prohibits you, for whatever reason, from sampling participants twice. So if you're measuring something like some skill or ability, or something about your hypothesis requires that the participant not be exposed to your treatment conditions more than once, then even if you're using simple random sampling, you're going to have to use without replacement. But regardless, of course, with replacement is going to be the best for eliminating bias, but they are both kind of the gold standard of sampling because they result in the least biased sample. Okay, this is the sampling technique that has the lowest probability of resulting in a biased sample. Now, it doesn't mean you have a guarantee, because if you were sampling those 8th graders in a very non-biased way, simple random sampling, you could still inadvertently draw out for your sample of 20 some of the most brightest kids in that target population, or some of the kids who struggle with intellectual disabilities. Okay, that can still happen. This just results in the lowest probability of that happening. So right now what I'm going to show you, I'm going to skip through these because I'm going to come back to them. These are the other probability sampling methods. When I show you the little graphic, it's a little grainy, but it's a visual of simple random sampling. So here you have this target population of all these variegated people. You got people of all genders, of all ethnic groups, of all ages, of all sizes. And it's not just demographic characteristics, it's characteristics that you can't see. You've got people who are more depressed and less depressed. You've got people who are happier and sadder and angry and aggressive and kind and sweet, whatever, internal and external characteristics. If you choose participants from your sample in a simple random way, you are most likely to have a sample that contains those characteristics distributed in a way that's very similar to the way they are distributed in the target population. And I'm going to say that again because it sounded really good. I don't know if I can. And it's true. If you use simple random sampling, you're most likely to acquire a sample that has all characteristics distributed in a way that it is distributed in the target population. End. All right. So back here. That is simple random sampling with and without replacement. All right. I think I have time to do the second type of probability sampling, which is called systematic sampling. Now, as we go through these sampling techniques, you're going to see that each of these, of course, in the probability sampling category, require a known, calculatable, accessible target population. You got to know the number of them, but they introduce a little bit more sampling or bias as we move along. With systematic sampling, there may be some reasons that you aren't going to be able to use simple random sampling. And so use a little bit different technique. And I think I can show you this best. Again, I'll come back to these, but I have a graphic of this that illustrates it very well. So let's say I have that target population of 100 8th grade middle school students, and I want a sample of 25 of them. Okay, so I want everyone to have a roughly 1 in 4 chance of being selected for my sample. But I have a list of all the participants, and I need to quickly get some people to contact to be in my sample. So I have this list, and what I'm going to do, and they're numbered 1 to 100, what I'm going to do is choose a random number from 1 to 100. Okay, I can use a table of random numbers. I can use a computer generation of random numbers. I can pick a number out of a hat, whatever. I'm using a random procedure. Or I pick a number. Well, oops, I picked out the number 11. Okay, well, that tells me I'm going to start at the 11th person on the list, person number 11th, go down to number 11. And then, because I need a sample of 25 out of the 100 people, I'm going to select every fourth person on the list. If I wanted a sample of 20, I would select every fifth person on the list. Does that make sense to you? So I'm going to go and choose every fourth person. Now, as you can see, this violates both independence and equality. So every person does not have an equal chance of being selected for my sample if I use this technique, because by looking at this graphic, you can see that person number 15 has zero. I'm sorry, no, person 15 is going to be selected. Person number 12 has zero chance of being selected for my sample. So they don't have an equal chance. I'm violating that, okay? And I'm also violating independence because the inclusion of a person in my sample is dependent on where they fall in the list, okay? That is systematic sampling. Now, it's also a pretty good sampling method, and it will reduce amount of bias. There's still an element of randomness in it, right? Because you're randomly choosing the number where to begin on the list, and the list is hopefully not organized. And, you know, you could make sure about that the list is organized in some random fashion. It's not systematically organized, let's say, by, you know, classroom that the kids are in, or already listed in order of present intellectual functioning, something like that. Okay, so that is systematic sampling. With that, we have arrived at about 56 minutes. So I'm going to stop and I will pick up with stratified random sampling in part 2. Until then, have a great day.